Okay, thanks though very much, and it's my honor to be here. And today I would like to talk about our recent thinking on the network representation, revisiting the big data era. So because I'm still suffering from serious jet lag, so please forgive me if I stuck. This is the most difficult time. So actually today, everybody talk about big data, right? Big data, we think that big data is a challenge, not only because it's big. So of course, we can see that the data volume exponentially grow with the time, but at the same time, we should also see that the computing power also exponentially grow with the time, right? So it seems that there is no big problem here, right? But there is an argument that it's not a big problem only if the data is unlinked. So what if the data is linked? If the data is linked to each other, then the required computing on this data should be exponential with the data scale, right? If the data scale exponential grow with the time, then the required computing actually is doubly exponentially grow, right? So between the provided computing, the exponentially grow, and the required computing, the doubly exponentially grow, there is a serious gap here, right? So we think that the real big data problem resides in the linked data. And in real cases, actually, most of the data is linked. So we can see that people are connected to form the social networks, and the genes are connected to form the biology networks. And even the photos that we take every day, they are linked by the metadata, for example, the location, the time, and also in the same event. So they form the visual web. So we can see that the networks are actually the natural representations for such kind of linked big data. So we need to do some network analytics to mine the value from such linked big data, right? For example, the node importance, the community detection, link prediction, and also node classification. So we think that this kind of net analytics technology actually have very vital impact on many real applications, such as recommendation systems and also the operation optimization problems. But the adoption of this kind of advanced network analytic technology actually is not very optimistic in real cases. So we know that in Tencent, they have the billion scale social network. And in Taobao, they have billion scale e-commerce network. So when I discussed with engineers and the researchers in the Tencent and in Taobao, I found that they just use very simple network algorithm or even some heuristic rule to deal with the network data. So I just say, hey, we have a lot of advanced network analytics algorithms that can definitely improve your performance. They say, hey, buddy, just run your algorithm on our billion scale network and give us a response in an acceptable time. Okay, we know that it's very challenging, right? So today, actually, the network have grown into such a scale that no sophisticated network analytics is doable. So what is the bottleneck? So given a network, actually, we usually represent the network in this form, right? A vertex set and an edge set. We think that it is the link that gives us a lot of difficulty in dealing with the network data. So because of the link, actually, a lot of network analytics algorithm is iterative or combinatorial. So for example, in this network, if we want to measure the importance of this node, they will require us to first calculate the importance of the older neighbor nodes, right? So this is actually spread out in an iterative way. So the algorithm will be very complex, right? And also because of the link, the nodes are coupling together. So it's not easy for us to parallel the network analytics in different servers, right? And also because of the link, the node and node are dependent. So it's very difficult for us to use traditional or classical machine learning methods to deal with network data. So we think that the link information actually is a bottleneck for the network analytics. So we want to ask whether this is the only way to represent a network. In most cases, actually, underlying each network, there are often a low-dimensional vector space. For example, if we are in a social network, if two people are connected, actually there must be some proximities in this kind of low-dimensional vector space. For example, they share similar social attributes or they share similar preferences, right? So actually, this is the source of a more intrinsic representation of this kind of network. So the problem is, given this kind of network, whether we can embed back to the low-dimensional vector space. If we can do this, then the node here is still the node here. But the link here is replaced by the distance metric in this kind of metric space, right? And if we can transform the network into this kind of vector space, then it's easy to parallel because dots and dots are independent. And also, we can apply very classical machine learning methods to deal with network data, right? So this is a main idea. So the ultimate goal for the network embedding, actually, ambitiously speaking, we think that the embedding space should not only can reconstruct the original network, but can replace the original network in all these kinds of network analytics. That means that we want the embedding space can support, we do all this kind of network analytics in the vector space, not in the original network, right? So this is our ultimate goal. So how can we do this? We think that the vector space should be able to meet these two goals. First, as the vector space should be able to reconstruct the original network. And the second one is the vector space should support network inference. And also this actually are the goals for our network embedding methods. So actually network embedding is not a new idea, right? So in the past works, actually we call them the network embedding 1.0 because most of them focus on the first goal to reconstruct the original network. So for example, this is a matrix factorization actually is a typical method for network embedding. So given a network, we can represent the network with the adjacency matrix, right? So after we do SVD on the adjacency matrix, we can get the embedding matrix for each node, right? So if we see the objective, we can see that this kind of methods actually, they aim to reconstruct all the observed links. That means we want to find an embedding space that overfit the network, right? In such an embedding space, the network inference ability is actually seriously limited. So what we want to do is to lay more emphasis on the second goal to support network inference. So there are two problems here. One is to try to find an embedding space to reflect the network structure. And the second is try to find an embedding space to maintain some important network properties. For example, the network transitivities, right? So for the network structure, actually there are two very important and very commonly used network structure features. One is the first order proximity that tells whether two nodes are linked in the network. And also the second order proximity that is proportional to the number of common neighborhoods between every two nodes, right? So the problem is how can we simultaneously incorporate the first order and the second order proximities in the embedding? So here we have two objectives. One is we want to find out an embedding space to reconstruct the network. And the second one is try to preserve the network structure in this embedding space. So there have been some previous research that has demonstrated that the underlying space of a network actually is highly nonlinear. So we think the transformation from the network to embedding space actually should be a highly nonlinear function, right? But in the previous works, most of them are based on shallow models. And we all know that shallow models actually cannot well capture the nonlinearity of the data, right? So there is some problem here. And also some previous works just use some manifold learning methods to address the nonlinearity problem, but they just ignore the structure information, but only focus on the node and the link information. So here, we think that in recent years, the deep learning models has been demonstrated to be very effective to deal with a nonlinear problem, right? So our initial idea is try to propose a deep model for network embedding to address the nonlinear problem. And at the same time, we try to incorporate the structure information into the learning process so that the learned embedding can incorporate both the first order proximity and the second order proximity. So the challenge here is that most of the deep models are designed for vector space data, for image, for video, for text, just a vector space data, right? How can we deal with the network data with the deep model, right? This is actually a fresh area. And the second one is how can we preserve the first and the second order proximity in the deep neural networks, right? So based on this thinking, we propose deep model for structure preserving network embedding in this year's KDD. And actually in this network, we just represent each vertex with its neighborhood vector, is a adjacency vector. And then this is actually an autoencoder. In this autoencoder, we try to learn a low-dimensional representation for each vertex neighborhood. And the objective is this low-dimensional representation can reconstruct the neighborhood vector. So here we can see that if two vertices, they have similar common neighborhood, then they will have similar latent representations in this framework, right? So in this way, the second order proximity is incorporated. And also we impose the Laplacian eigenmaps here to constrain the first order proximity. That means if two nodes, they are linked, then we constrain their representation should be similar. So in this way, the first order proximity is incorporated, right? So in this kind of deep neural network, we can incorporate both first order and the second order information. So after learning the representation, we try to evaluate this, the effectiveness of the embedding in both the network reconstruction and also network inference. So in the network reconstruction, we can see that the proposed deep learning models actually can achieve the best performance, right? No doubt. And for the network inference ability, we use a link prediction to evaluate it. So I want to mention that here in archive data, actually the learned embedding can achieve 100% accuracy in predicted the top 10,000 links. So actually this is very impressive, right? And also we can see that on the black catalog data, our method can achieve 2 times higher precision than all the state-of-the-art link prediction algorithms. I want to say that here, the line and the graph, actually they also incorporate first order and the second order proximity. So we have to attribute the significant improvement to the power of the proposed deep model, right? So actually from this work, we can conclude that the structure preserving actually is essential for network representation learning. And I want to say that deep model actually have very large potential in dealing with the network data. So actually, I think this is actually an opportunity for our KDD community. And also, it's possible to realize various network applications in the embedding space. Then let's move to the second part, try to maintain some network property, the transitivity. So the transitivity actually is a very critical property to support network inference. The transitivity phenomenon actually is also very ubiquitous in the network domain. For example, in this network, A and B has a link and B and C has a link. Then A and C is very possible to have a link, right? So this is a network transitivity. And on the other side, actually in the embedding space, there also the transitivity phenomenon also exists in the embedding space. And this is actually guaranteed by the triangle inequality. Right? If A is close to B and B close to C, then A is relatively close to C. So it seems that two sides perfectly match, right? But the real problem, the real network data is actually more complex than what we assume. So one of them is that we observe the asymmetric transitivity in the directed network, right? So in this kind of directed network, if A has a link to B and B has a link to C, then A is possible to have a link to C, but C is less possible to have a link to A, right? The transitivity is asymmetric. And we also observe that the asymmetric transitivity actually do exist in the real data. And we also find that this kind of asymmetric transitivity play very important roles in the link formation in directed networks. So the problem is the distance metric in the embedding space actually is symmetric, right? So how can we incorporate this kind of asymmetric transitivity in a symmetric space, right? This is actually a very challenging problem. So in the past work, actually, there is no sound solution, right? So in this case, if we give each node a single vector, in this, for example, A is similar to B, B is similar to C, then A will be similar to C in both directions, right? So the asymmetric will fail. And if we give two vectors to one node, that's a source vector and a target vector, then in this case, let's see that source A is similar to target B, and the source B is similar to target C, right? So in this case, actually, we will not have any constraint on the source A to target C, right? So in this way, actually, the learned embedding of source A and the target C will not be necessarily similar. So in this way, the transitivity fail, right? So actually, how to address the asymmetric transitivity problem in directed graph is an open problem. So by extensive study, we finally find that the high-order proximities are adequate asymmetric transitivity metrics. Let's take the CAS similarity, for example. So CAS similarity calculates the weighted sum of parses between any two nodes. So in this case, we can say we can see that A to B is 0.3, B to C is 0.3, and A to C is 0.18, but C to A is 0. So this actually totally coincides with our requirements on the asymmetric similarity, right? So it seems that we can have a straightforward solution. We just use the traditional matrix factorization framework. The difference is the high order, the adjacency matrix in the past is replaced by the high order proximity matrix. And after we do SVD on this matrix, we can get the source embedding and the target embedding, right? So actually, the problem is not that easy. The main problem is the calculation of a high order proximity is not scalable. So take CAS, for example. If we want to calculate CAS, the time complexity is n cubed, and n is the total number of nodes in the network. So we can see that it's impossible for us to calculate the CAS in a billion scale network, right? So that it's not acceptable. So fortunately, through some study, we finally find that most of the representative high-order proximities, the CAS, the personalized PageRank, common neighbors, endemic ADA, actually they share a general form. The general form is all of them can be transformed into a product of an inverse matrix and another matrix. So what's the power of the general form? Given this form, actually, some mathematical tool, for example, the generalized SVD actually can decompose S without calculating S. That means for this kind, if we want to get the SVD result of S, we can this result actually can be approximated by the SVD result of MG and ML, so that the time complexity of this operation can be reduced to linear with the H number. The H number is the total H number of the network. Actually, it is linear with the data volume, right? And also, the GSVD can provide us theoretically guaranteed upper bound for this kind of approximation. So we can use the GSVD and to do the high order proximity approximation, and further to do the asymmetric transitivity preserved graph embedding. So let's see the result. We evaluate the learned embedding in two tasks. One is a high order proximity approximation. So this is our method, and this is a state-of-the-art high order proximity approximation method. We can see that our method can reduce the approximation error by about 95%. So this is a very impressive number, right? And actually, PPE, they just use, because the complexity is very high, they just use some sampling-based method. And we actually, in contrast, we do this by a theoretical guaranteed solution by the GSVD, so we can solve the sampling bias and the sampling size, scale problem, right? So this improvement can be attributed to the GSVD and the high order proximity approximation. And further, we evaluate the embedding in the network inference, more specifically the link prediction. We can see that the non-transitivity preserved asymmetric transitivity preserved embedding can boost the link prediction accuracy by 2 times and 4 times in very large scale network. And here I want to mention that in all of these baselines, we can see that there are some baselines that is applied in a regional network. For example, the common neighbors and the atomic data. They are actually some methods that is applied in the original network. So this improvement means that in the embedding space, actually we can get even better performance than the original network space. So I think this is a very promising direction. So from this work, we can conclude that the transitivity as a very representative network property is very important for network representation learning. And also the incorporation of these properties are especially important for network inference tasks. So finally, I would like to summarize my talk. And the network data is, of course, very important, but now it's undermined in real applications. So the bottleneck and the main problem is the complexity and the scalability problem of network analytics, right? So a fundamental solution is fundamentally try to do some research to propose some network representation learning for a more effective and efficient way to represent networks. And the network embedding has been demonstrated to be a promising way, but we still have a long way to go from the network embedding 1.0, the network reconstruction, to the network embedding 2.0, to structure preserving and even property maintaining network embedding. So before ending this talk, I would like to acknowledge all of the students that work on this topic, Mingdong O, Daixin Wang, and Ziwei Zhang. And also I would like to acknowledge all my collaborators on this topic, Shiqiang Yang, Wenwu Zhu, Jianpei, and Fei Wang. Without their valuable comments, we cannot get these achievements. So thank you.